So, a big welcome to the lecture Multimedia Databases. As you all know, this lecture is going to take place in English language, and we do have recordings of that lecture. So, at this moment, we are actually recording what I'm saying and what I'm doing here, and all the markups and whatnot. So you kind of like can follow everything I do online. After the lecture, we will take the slides and all the lecture courses to our website. And all interesting information will be on the Institute's website. So we do have a website at the Institute, EFIS, and there's a sub menu teaching, and if you go there, you will find the lecture and everything that is important to the lecture. So we will not only have all the slides there, but we will also have papers that give you additional insights, or the selections of books, or exercises or whatnot, all on that page, right? So this is the single-stop shopping. So first some organizational issues, and then we will spend the rest of the lecture with what this lecture is actually about and what you will learn in this lecture. As you will have noticed, we do have a longer lecture. We don't have the usual 90 minutes, but we do have 45 minutes on top of that, which is because we integrated the exercises into the lecture in the form of detours. So detours is a concept. Who has never heard any of my lectures? Detours is a concept where you can sit back a little bit, you know, like this is for giving you deeper insight, for telling you more about the background issues or historical developments, how it came to be in a certain way, or certain applications where you can see how what we worked on is actually applied in practice, right? So this is not stuff that is necessarily important for in the algorithmic sense, or in the sense of, you know, like you have to deeply understand that, but this is stuff where you can kind of like get a little bit of background information and then see what people are doing with that thing. So that is integrated. We will have a short break in the middle of the lecture, so you can relax a little bit. This is a 5-credit lecture, and the exams, I mean, seeing that it's now like 20 people, right? 6, 8, 9, more than 20 people actually. We will have to look how many stay and how many come. Usually I do oral exams, which is the easiest way for everybody. But if it gets more than this, we will probably have to do written exams. So usually the break-even point is 25 to 30 people. From when on, written exams become more probable. So there will be occasionally homework, so exercise sheets, and I advise you to do them. They are not a prerequisite, but they give you some deeper insight. They let you play around with some of the concepts so you can understand them more easily. I see. Recommended literature, of course, is there. You can either get it from... Yes, please.
Are the exams in English as well?
No, whatever you like. Whatever you like. If you prefer to be in English, we can do that. If you prefer to be German, no problem whatsoever. You know, like, this is an English-speaking language, an English language lecture, because it is part of an international course of studies, the Internet Technologies and Information Systems course of study, of which, how many people are here? No? Ah, there you go. So some people are actually there, and some people follow the things online from University of Hanover, Clausthal, or Göttingen, that are also part of that course. And so we will do it in English. Moreover, I usually do slides in English, because in computer science it's kind of like very difficult sometimes to get German words for what is described there. You know, like, I mean, if you're talking about conditional random fields or something like that, that goes on very easily, but you know, like how they are called in German, I have no idea whatsoever, right? And even if there is a notion for it or a word for it, I always like the example of recovery systems and normal databases, right? You know what the German term is?
No.
Ah, there you go, right? Ein Wiederaufsatzsystem. And this is scheußlich, as we say in German, right? So I'm kind of like bound to use English terms anyway, and then it becomes kind of Denglish, so we can immediately do it in English. But of course, for the exams, right? If you want it to be German, and you can express yourself more easily in German, no problem whatsoever. We can do it in German or in English or in any mixture that you like. Good? Other questions? Yes, please.
We have an hour after it is a practice hour, something like that. Will that take place or not?
What do you mean a practice hour?
We have Übung. Wir haben eine Übung nach dieser Stunde, glaube ich.
Yes.
Is that put in this hour now, or will that take place after this?
Well, that's basically what I was telling you before. That's kind of the concept of detours. So we blend in the exercise with the lecture. So it can happen at any point in time. This is usually just 3 hours of lecturing, right, with a short break in the middle, right? And at some point where it fits, we will do the exercises in terms of these detours, you know, where you can see some applications, where you can see how it actually works, or we show you examples, simulations, or something like that. So you can see what happens, right? And I find it in a way much more sensible to do the lectures or to do the exercises when they occur, you know, like when you're actually talking about the stuff, than doing it in a different venue, you know, like 3 days later and then come, oh, do you remember we had this thing there and this is what I want to do an exercise about, right? So I rather prefer it to be, you know, like on the spot, so that you get the full feeling. And everything will be online, everything will be, the exercise sheets will be on the web page, the videos will be on the web page, so you can kind of compare between them, you can look at them, so all the media is there. Okay? Yeah. Any more questions? Nope? Very good. Recommended literature. There will be a couple of books that I usually recommend. There's no book kind of covering the full course because we're doing different things. We're doing video retrieval, we're doing audio retrieval, we're doing image retrieval. So we're kind of like covering all kinds of media that can happen in databases and that happen, Morgan, and that happens very often nowadays, right? So you have a lot of applications like Shazam or SingStar, you know, like that use multimedia technology in the database sense. And I will tell you in this lecture how they work and how to build such a thing, right? We will also, you know, all know YouTube and things. We will talk about how it works. We will talk about how to check for duplicate content or something like that in YouTube. We will talk about images that are prime media for exchanging information these days, right? And we will talk about how to index them. We will talk about how to store them. We will talk about all these issues from a database point of view, right? And yeah, so for the literature, I have looked for different kinds of books. There's Ähnlichkeitssuche, there's a German book, Ähnlichkeitssuche in Multimedia Datenbanken of Ingo Schmidt. That's kind of like a theoretical work where most of the basic notions are clarified, and so this is kind of nice to read. The classic book is Ralf Steinmetz, Multimedia Technology, comes in German or in English, so there are both language versions of that book available. A little bit more specialized is Castelli-Bergmann image databases, so they only cover image, but they cover it in a depth that we can't do in this lecture, otherwise we would have 2 semesters or 3 semesters, right? Because they kind of like do everything you can do with images. where we only spent 6 weeks or something like that on images. Interesting book. Then there's Khoshafian Baker, Multimedia and Imaging Databases, a little bit broader view of the things. And sometimes on our webpage, there will be the original research papers of some of the algorithms, of some of the methods that I'm describing. But whenever we interlink original papers, they are kind of easy to read. They are not too deep, so you can kind of like understand the basic concepts in them, and you will find further information there if you need to program something or if you get an idea to play around with something, right? So you have all the resources that you might need. All these books are available via the library, or we do have a small library in the EFIS Institute. So if you want to look at any of the books, or if you need any input from the books, we just have 1 exemplar per book in the library, but you can always ask any of the assistants to get a key to the library and then work there, no problem, right? So that is literature. Then I was already talking about the course, the course webpage. That is kind of like the course webpage where you find all the information. So it's in our normal web page under the menu item of teaching. You will find all the semesters, and this semester you find multimedia databases, and everything you might want to see is there, including the videos of what we do now. If there are any questions, drop us an email, right, or just stop by. Usually there's always an assistant, or even I am around, right? So if you have questions, if you have anything better now or better when you experience the question, than just before the exams, when you're kind of like not getting further with your preparation of the exam because you didn't understand something, right? So whenever you like, just drop by. Good. Any more questions for the organizational part of the lecture? Nope. Then I will tell you what all this is about. And this is the topic of today's lecture. So what we're trying to do in the first part is we're trying to close in on the question of what actually are multimedia databases and why is it important to look at them in such a lecture. We will also give you some applications, and in the end of the lecture we will talk about how to evaluate the correctness of multimedia retrieval, because you will see that it's sometimes difficult, right? It's not as clear-cut as in the relational databases, RDB1, you know, like where you had SQL and everything was clear and everything was crisp. Multimedia databases are a little bit more problematic, because you're dealing with media that is open to interpretation, right? And there might be different interpretations giving you not a yes or no, but a maybe or a rather, right? And this is kind of an interesting thing that we will talk about later on. So if somebody puts the question out, what is a multimedia database? The first answer I would give is, well, it's a database plus multimedia, right? So it's a database where you put media in. And that's basically all of it. And media can be images, video, audio files, whatever, right? And we all know databases, we all love databases, right? Everybody has heard RDB1, have you? Who has heard RDB1? Yeah, most of them. So you all know kind of like SQL style databases, you all know tables, but how to put an image into a table, right? Does it work? That's kind of not as easy as it looks. So let's go back to the multimedia part of the databases. And what is multimedia? And multimedia is actually the integration of different digital media types. And integration means that you can put things together. You can have text, you can have images put together on a single page, right? You can have active objects within that page, within that document, right? Where you can embed a video, right? No problem these days. So all the integration and all the mixture of different media to get the point across, whatever you want to do, whether you want to teach somebody, whether you want to share experiences, for example, of your recent holiday in Spain or something like that, right? It will usually be a mixture of different medias that you have. And then the basic media type are text, which is kind of like carrying a very simple semantics, the semantics of spoken language. Images, which can express different semantics. Some people say an image says more than 1,000 words, right? And it can also transport feelings, for example, or moods. There's vector graphics, if you think about the scientific applications, right? So CAD or something like that, where you have architectural sketches or plans for building machines or something like that. It can be audio files, so you played on the guitar sitting on the beach of Spain and you want your friends to hear that, right? Or rather not. There's video, so kind of like different media types like images and audio coming together in a timely fashion, right? So there's different kinds of media that can be used, and for all these different data types and for all these different media types, you have a lot of applications where these things typically are used, right? So for text, you have the classic web pages, for example, but could also be Excel spreadsheets, you know, like calculations of something. Could be emails, right? So all kinds of things. Images can be photos, can be vector graphics, CAD, what you have, right? Audio can be speech recordings, music recording, but can also be annotations, right? So what I'm doing here, you get an audio track of with respect to the slides, right? It comes in different formats and different types. There can be WAV files, MIDI files, MP3 is one of the reigning formats at the time. So there's video files, right, which is kind of like has a time description, so it's a dynamical image record. You have sequences of frames, sequences of individual images that are just put on top of each other, but there's also things like edited movies, right, where you have a lot of scenes and a lot of cutting going on that can be like in a feature movie, in a cinematic mode where you usually have longer scenes, or there can be a music video where you usually have very short cuts and very small image sequences or very short image sequences, right? And also there's a multitude of different formats that can come in. For the documents, well, usually within a document, if you're talking about the media, if you're talking about an image or something like that, then you just refer to only one type, right? Then you just refer to the object as such, right? But in multimedia, documents, compound documents, complex documents are allowed that include a lot of these different media, right? And if you look at these courses that we do here, for example, you do have already different media. You have the video that we're doing, you have my audio track, you have the slides, you have the exercise sheets, you have books or recommended literature, which is textual, but also contains images again, right? And so on, and all these media is interconnected somehow, right? Because what we do here is we take content from books, from libraries, from personal experience, from whatever, and we edit it so you can get a course, right? And this editing, I mean, all this talk about MOOCs these days, right? So everybody is on about MOOCs. We don't need universities anymore, right? We have the iVersity, right, where I learn what I want to. And we have MOOCs so that everybody can be taught by Nobel Prize winners, right? And only have very good courses. And it makes me wonder why they did not abandon universities kind of 1,000 years ago, because then we had libraries, right? So everybody could read up what he or she wanted. So why do we need universities as such? And the reason is quite simple. What a professor does, or what the coursework does, is editing. We're editing information out of the flood of information that is around you, so that you get a sensible syllabus, right? That you get things that connect somehow. And who has heard the multimedia lectures of Lars Wolf? Nobody yet in networking? Okay, good. You will find that a lot of the things, that a lot of the topics do overlap, right? There's usually a different perspective. So we talk about the storage and the indexing of videos, for example, or how to determine whether videos are similar. He talks about the transmission, the broadcasting of videos, right? And different schemes of how you can do that in an efficient way, right? So video on demand, for example. But it's kind of like we're using the same kind of features. We're using the same kind of aspects of this common object video or images or whatever it is. And also, if you go down to computer graphics, right? They're using similar things. So, for example, the fingerprinting techniques that we use for indexing are very often used in computer graphics for describing things and for altering things, right? So that's what's happened. Basic definitions, some basic definitions that we need. So if I talk about media, I'm talking about a basic medium, and the medium is a carrier of information in a communication connection. So an image that is just lying somewhere is helping nobody. You have to look at it, and then it should transport some information. Exactly. That makes it a carrier of information, right? And basically the type of the medium is independent, is orthogonal to the transported information. You don't know what the image is about, right, until you see it. And there are a lot of things that you can show on images. And sometimes it's kind of like interesting what you can show on images that you didn't think about, right? During the information transfer, the medium can also be changed. So, for example, if you look at video, very often you're shown a couple of keyframes, a couple of still images, to get a feeling of what this is about, and then you want more information and you're starting to watch the video, right? We will also talk about these kinds of changes. Classic example for a medium, we were already talking about libraries, is the good old book, right? And the book moderates a communication between the author of the book and the reader, right? Without them knowing each other, without them kind of like having ever met. But the author is of the opinion that what he or she writes is important to know for the reader, or is educating the reader, or is entertaining the reader, or is doing anything else what the author wants to express to the reader, right? And the reader, on the other hand, is of the opinion that it's valuable to read that book, or it's entertaining to read that book, or the reader just feels to read that book for whatever reason, right? So this is a asynchronous, but still communication between author and reader. It's totally independent from the context, so there are books about virtually everything, right? And it's hierarchically built on text and images, so usually here already media can be mixed, and you can also change the medium. So, for example, if you read a book to somebody else, you're transporting the medium book into the medium sound, and then you're kind of like reading the book. The information that is transported is the same. Is it really the same? Well, if it's text, yes, probably yes, right? Because you can argue that it's a very beautiful type or very nice font or whatever, right? That gives some extra feeling when reading the book, or it's just nicely written in a certain way. There are some expressionist poets that kind of arrange text in certain patterns so that you can see which is lost when you read it out loud, in a way. It's more easy to see that something is lost when you talk about images, right? Because the impression of an image, or describing the impression of an image in sound, is difficult. It's very hard what you actually see, how you go on to describe the image, how you go, what are you telling the user about an image, right? And this is kind of something that we will explore a little bit. You can classify the media based on the receiver type. So there are visual or optical media, like the images. There are acoustic mediums, like the read out text. There are haptical mediums, so where you can feel something. Haptic interfaces are becoming modern these days. Probably many of you will know force feedback joysticks, or kind of like devices for gaming, right? This is a typical haptical medium. There's olfactory media. Olfactory means smelling, right? So some of you may still know these scratch and sniff things, kind of like where you can scratch something, then you get a certain smell. There was always talk about kind of doing it with television, so that you can kind of like get the right smell at the cooking session, right, with Jamie Oliver or whatnot, right, and then you smell the fresh salad or the roast or whatever he is doing, right. There's gustatory media where you can experience things to taste. Very few of them make sense, but they're around there, and you sometimes see them in art. They are based on time, right? So you can say there's static media, like an image. There's also dynamic media, like a video, right? Or an audio recording that have a notion of time, right? Whereas texts or images do not have a notion of time. So we've seen different ways of building multimedia, and we see that multimedia is always a necessary aid for communication, for communicating content, for kind of like telling people something, right? Of course, the question remains, good, we have this multimedia and we can use it and we can read the book or something like that. Why do we need database, right? Why do you want to do that course? And one of the reasons why we need the databases, I mean, databases are about storage and retrieval, right? You put something into a database and you get it back with a query from a database, right? And this is usually only necessary or only sensible if you have a lot of objects that manually sifting through gets very tiresome and very difficult, sometimes even impossible. I mean, how many of you know the Librerei, the Andriana here? Oh no, nobody? Interesting. It's a small building. It's actually a very small brick building, just behind the Church of St. Andrews at the Wollmarkt, right? So behind the Andreaskirche, and it is actually one of the first public libraries in Europe, right? So it dates back to the 14th century or something like that, quite old. And if you look at it, it's like maybe like that space here where I'm standing, right? So it's rather small. And you think, this was the first public library? I mean, come on, how many books could they have had, right? If there were 100 books in there, I would already fill up quite a lot of the space, right?
Depends how tall it is. It can also depend how tall it is.
It's not very tall. It's 2 stories, but still, I mean, it's not you know, like it's impressive because it's old and it was the first public library, you know, but it's not impressive by the size. You know, it's nice, but you know, like look, oh yeah, it's kind of tiny, and at that time it was not a problem because they did not even have 100 books. Right? Books were a very rare good, a very important good, but the idea to make them public, the idea to make knowledge that is written in books public, that was the interesting point. And of course, you didn't need a database at that point because everybody could see, you know, like, okay, these are 100 books or something like that. I can go through them, I can find everything. Nowadays, we don't have 100 books, right? I mean, you have more than 100 books on your smartphone probably, or on your ebook reader, right? So you carry more than the Andriana ever had in your bag, and this is what needs the database part, right? We need the storage on one hand, but more we need the retrieval. We need to be able to query the information. And given that we have a lot of publications coming out every 5 minutes, right? So a lot of research by different universities all around the world in different languages, in different styles. You know, like multimedia is becoming more important than ever. Good. So for the storage part of the media, well, that is one of the problems because text is easy to store, and textual representations of documents are quite kind of small. When it comes to images or to video, that's rather big, right? So that's already big volumes. And I saw some estimations of the size of YouTube and what they have to store. Right, it's amazing. We will look at that when we do the video part, right? It's amazing how big that is, right? And you need special techniques to do that. So the storage part is hard. The retrieval part is, in my opinion, even harder because what you usually use for retrieval is not only the metadata that you say, oh, this is a picture of Leonardo da Vinci and it shows the Mona Lisa and it hangs in the Louvre or something like that, right? But how do you describe the image? I want an image that looks like this, right? Or I want an image. There's a woman on it and a city in the background, right? How do you find these images, right? Do you describe them? And that is something that is still problematic, but to some degree can be solved. And it's not only images, right? It's also music, for example. You know, like you hear this new wonderful thing in the radio. You know, like and you want a copy of that song. You have no idea what it is, so you start on humming this song that goes like right? And the guy in the record store says yeah, we have that quite a lot of times actually. Actually, things like that, we will talk about how this can be done, right? And you see some fun applications of that. For example, how many of you have played SingStar or something similar? Well, there you go, right? Do you ever wonder how it works? We will talk about that, right? We will try it. So the search to some degree should be based on the content, on what is expressed by the thing. On the other hand, of course, it is important who painted the picture, right? Or I want all the pictures of Claude Monet or something like that, right? Queries like that do exist. So we do need some metadata here. We do need some annotations of the objects. And there are actually some standards, MPEG 7, MPEG 21, that have been specifically built for describing these objects, and there are different standards for different kinds of objects. There's always the question between a standalone or a database storage model. So how do you store it? Are the actual media, is that an integral type of the database? Is that an object that is directly stored in the database, or do you store it on some media server, right, and just interlink it with data from the database, right? And both has advantages. So, for example, for the for the search possibilities. Having the thing at hand within the database offers a more flexible search algorithms where people can actually use their own algorithms or their own parameters to do that, which might be difficult if it's stored offline, right? So if you have just the metadata. In any case, what we want, if we have it within the database, is that we can carry over many of the advantages that we have with databases. An SQL-style query language, which is easy to express things with, you know, like, so the orthogonal combination of query functionality. So the selections, projections, and joins, you know, like they mix with each other in every fashion that you can imagine, right? So you don't have this kind of pattern that you always have to follow, but you can build your own queries. You have all the query optimization going on. You have the indexing techniques that have to be adapted because you want fast retrieval. You have transaction management. You have recovery of the database, right? All these wonderful things that we learned to like in RDB1 can now be transported to media storage, right? And this is why a database solution kind of sensible. So actually, to give you a short historical overview, databases are nothing new, right? So databases evolved in the 60s, basically for the banking and insurance companies, but also for capturing information. So for example, for NASA's space program, the Apollo program, where the first database by the first...
Storing Panama Papers information.
Yeah, I mean, sifting through that must have been very tiresome and a lot of manual labor, actually, right? If they had it in a nice database, it would have been better, probably. But I'm quite sure they put it into a database afterwards, right, for easy reference. Anyway, so the first time people became aware of the problem was written texts, right? Books, natural language. And that was different from the banking, that was different from the insurance companies, where you had account numbers and where you had kind of like a balance and you withdraw money and then you kind of like put money on the account or something like that. Easy operations. Handling books, handling written texts is different. And there was actually a research area, information retrieval, that split from the mainstream databases. The mainstream databases went on over the 70s and 80s to work on different models, to work on optimization, to work on scalability, whereas the information retrieval people had to look at text features, you know, like, and how to work with spoken language, you know, natural language processing. That was part of their work, right? So there was two communities that sometimes met, right, and that sometimes had something in common. But it was not really all the rage. And when in the 70s and 80s, the relational databases and SQL style databases were built and were hugely successful, there was not a lot of media, you know, like, I mean, when you had 64K computers, you don't talk about digitizing books and putting it in there, you know, or anything like that. That became kind of like interesting in the 90s, right? End of the 80s, where people began to dream a little bit larger and said, well, why don't we have digital libraries? You know, like, why can't we digitize all the world knowledge and put it in one place? Remember, the web was not invented at that point in time. That was invented in the 90s, right? And that is not by chance, right? It was just the time for these kind of revolutions where people were looking at the media on one hand and on the digital world on the other hand and try to bring it together, try to build tools. And that was the 1990s. That was probably the big time of multimedia databases. So most of the research, of the basic research that was done in that time is due to the 90s. And first multimedia databases came out 95, 96, something like that. And also the classical vendors, Oracle, IBM, Informix at that point in time, introduced possibilities to for their databases to work with media content, right? One of the thing SQL 92, which was one of the first standardizations, big standardizations of SQL, introduced blobs, binary large objects, right? Objects that were not interpreted, and that was used for images or something like that. But as I said, they were not interpreted, right? And the multimedia databases tried to work out how they could be interpreted, right? And this is interesting more in the general sense than in the pure specific database sense. Because what we will be doing in this lecture here is not merely about databases, but it's like a toolbox how to handle different media types. And you will see a lot of algorithms, a lot of different methods and tools that come from different disciplines like robotics, like image understanding or computer vision, computer graphics, right? And that is just used as a tool for making the database part of it happen, right? So we will see a lot of tools that are applicable in a lot of scenarios, and this is very open. This is what I like about this lecture actually, because it kind of uses a lot of different technologies, not only in the database sense. Good. Commercial systems, so the relational databases that are still all the rage nowadays, just have a data type for that, the blob, the binary large object. As I said, it's uninterpreted, and the retrieval was usually done due to metadata, right? So you had the file name, you could have a creator of that file, you could have the author or whatnot, right? But still the actual object is not taken into account. And the first way that these objects could be interpreted somehow, that was through object relational extensions. So many of you will know that the 90s were also the big time of object-oriented databases, right? So like in the programming languages, where people moved from C language, from the imperative programming style to the object-oriented programming style, that is still kind of standard today, right? And that was a kind of like a smooth transition in a way. People in databases tried the same thing. They wanted to go from the relational model to the object-oriented model, and that did not work. You know, never did. There were several very big vendors trying that, but they only could fill niches, right? So there was very small applications for what they were actually doing, and most of them worked with a remapping to relational databases in the end anyway, right? So that was all not native, and well, there were some native ones, but they didn't work either, right? So it was a big failure in the database community actually, right? And not all of it was bad, and this was why the vendors of relational databases decided to take some features that were nice about object orientation into their products, and this was called object relational extensions, right? So things like user-defined types, user-defined functions, stored procedures, right? So things that mimic the behavior of objects, that mimic some of the goodies that you get from object orientation, right? And for the multimedia part, the trick was semantic search, right? So you wanted to search media objects based on their semantics, based on what they expressed actually, what the image actually showed, or in what colors, or you know, like what the mood of the image was, or something like that, right? And several big vendors, for example, IBM or Oracle, built so-called extenders or cartridges to deal with these questions, right? And there was some integration into the database kernel through user-defined functions, user-defined types, and so on. That were the typical object relational extensions also used for media. the question of what you actually need for multimedia databases was discussed already in the 80s when multimedia databases were still a distant future, right? And only in the 90s people began to have the computing power to manipulate larger objects, right? And what is clear, or what was clear, is you want the classical database functionality, right? We want everything that we know from databases to be good, to be helpful. We want a nice query language, we want recovery, we want a transaction management, you know, like we want all the goodies. And of course fast, right? But one of the question was also about the maintenance for unformatted data. You know, how do you maintain that data? You had to consider the storage and presentation devices. I mean, retrieving relational data from a database and then getting back a table, or you know, like this cursor concept where you iterate over the result set, right? That did not really fit for multimedia databases anymore, because you need a video player or something like that to output the actual result, right? So you needed new tools within the database that would allow you to interact with the media, right? And for all these requirements to build on them, you need to look at a couple of aspects. So one is the question of the architecture, right? Do you need a completely new architecture for that? Do you need a native media database? Or is it just an extension of existing databases? So do you map it somehow to the relational model and everything works fine, right? How do you address the content, right? How do you identify objects? How do you describe objects? How do you refer to objects? Performance, yeah, there's people saying there's 3 important things about database, and that is performance, performance, and performance, right? And the faster a database is, the better it is, and the higher the price usually, right? And the typical things that you see is indexes, query optimization, and those are the holy cows of the database community, you know, like the query optimizer. Oh my God, never mess with the query optimizer. You might kind of like get bad results if you change anything, right? And this is kind of one of the issues. The user interface, of course, how do you interact with the system? Think about putting in an SQL query, easy, right? Select from where, blah, blah, blah. Think about putting in, I want an image like this. I want an image that looks like the Mona Lisa. Difficult, how do you do it? Graphical interfaces? Do you paint something, right? And saying, yeah, there's like the woman, and she's kind of, I will do the Mona Lisa, right? And the woman is smiling, you know, like a big smile, and then there's kind of like mountains in the background. So I'm not quite sure my system would recognize this to be the Mona Lisa, but there you go, right? So difficult. How do you do the user interface, right? Then, of course, the information extraction, right? How do you handle the media? How do you prepare the media to be ready for retrieval? I mean, obviously, you can't do at retrieval point when somebody says, "I want an image that looks like that." The database can't go into the collection and say, "Well, I have 1 million images, so let's look at them," you know, and then start to kind of like compare images pixel by pixel. You know, obviously, that will take hours. So not a good idea. We need to talk about storage devices, because media usually has a very, very high capacity, right? So video databases can grow arbitrarily big, right? So how do you control redundancy? How do you do compression and all that? Very important topics also for digital libraries. And then we should talk about information retrieval. So how do you integrate extended search functionality in classical metadata based functionality? That is, something is in the set or something is not in the set. You know, like with information retrieval, you usually have kind of like a ranking. You usually have this fits better, this fits worse, right? So this is what is going on. The change in the terminology is already in the term for querying, right? Whether in normal databases you would call it querying or query processing, right? In multimedia databases or information retrieval, you call it retrieval functionality, right? Retrieval, and a retrieval means that you choose between different data objects, right? Based on either a select condition, the exact match, like in the SQL fashion, right? I want an object that is a customer of the bank and whose name is Gerd Müller and who has an account number, I don't know, 4, 5, 6, 7, 8, 9, right? And there may be a tuple in the database or there may be not, but it's clear what that thing is. On the other hand, there might be the best match model, which is based on similarity, something that is most similar to this one, or that shares certain features with this one to some degree, right? And this notion of degree, this notion of you know, like being close to something, that is new. That is something that is very typical to retrieval, right? And the retrieval also has the notion of delivery. So how do you deliver results to a user, right? Usually you have this idea that the user knows a good result, when he or she sees it, right? And you see that, for example, in web search, a lot of the engines are giving snippets of the pages or maybe, you know, like some more information to make users kind of like decide or to make users choose which one could be more sensible or less sensible. So it's not just about inducing the ranking and then saying this is a first place object, this is a second place object, but also to give users some kind of feedback to figure out, you know, like, okay, understanding the query in this and this sense, you know, this would be a good result. Or understanding the query in a different sense, this would be a good result. Or there are a couple of good results, but they are somehow different. Maybe we can cluster them somehow. Maybe we can show different areas that you might want to explore, right? So also this kind of delivery is very interesting. Well, looking at the search functionality first, I already told you that the first search function has to be semantic. And what does semantic mean? Well, semantic means that there's some sense that is expressed by the object. And we're not looking at the metadata of the object, whether the song is by Madonna or something like that, but we're looking at the semantics of the thing, whether the melody is nice, for example, right? So that is some kind of semantics that is usually attributed by users, and that users usually see when they kind of like experience a piece of music or an image or something like that, right? So they will get a certain semantics from that. Same with images, right? If there's some animals on the image, we immediately recognize these are animals, right? So the semantics of the thing becomes clear to us, and we want to search on that semantics usually. And for that, we need an integration of the classical, of the set-based or metadata-based approach, right? This picture is by or has been painted by Leonardo da Vinci. And the extended functionality. This picture is showing a happy mood, right? So they are happy peasants kind of in the harvest or something like that, right? Or this has a gloomy mood, right? So this is rainy day in a gray city or something like that, right? So we get different ways, and we want to mix that. We want to have every combination possible. Important is also that the search does not directly access the media objects, because if it does, it becomes very slow. Right? Media objects tend to be big, and if at search time you have to go down into the media to really look at things, that is kind of like very difficult. May happen sometimes, but very difficult. So we need to extract some of the features, at least for a first choice of what to exclude from the first search, right? We have to normalize them so we can compare between different things. We have to index them so that we can quickly access some of them and maybe find out which are closer to a certain desired result and which are further off. And for that, we need, of course, similarity or distance measures, right? We have to talk about things being similar or things being the same, right? Or things being actually far away from each other. And we have to talk about that later on. So, typical example for content-based retrieval is retrieve all images showing a sunset or something like that, right? And then you look at different images, and I put some here, and actually that's the semantics is not quite clear, because this here is a sunrise, haha, right? Can you see the difference? No, you can't, because you don't know which way I'm pointing the camera. If I point it to the east, it's obviously a sunrise. If I'm pointing to the west, it's obviously a sunset, right? So it's difficult. Not all the information is captured in the image, right? But if I tell you all these were sunsets, you would probably believe it, and maybe it would be okay for whatever you have in mind, right? If you just want a nice picture as a background for your next party poster or something like that, you would not care whether it's a sunrise or a sunset, right? You would say, yeah, that looks like a sunset. So the question that we need for retrieval is, what do these images have in common, right? So what are common factors? So we can, for example, look at the colors. You see there are a lot of reds and yellows in there, like orange and so on, right? There's always the sun somewhere here, for example, right? But maybe there's no sun, like here, where it's a cloudy sunset. Maybe it's not a very good sunset, I don't know, right? So we have to look at common features, at features that describe the semantics being it's a sunset, right, of the image. That's the interesting thing. And that usually happens in two main steps, and I'm sticking to the image database here, right? You have a collection of images or media, right? And what you do first is you digitize them, right? You have to get them into digital format and store them somehow. Then you look at what you want to search on. What are the descriptive features of that image, right? You analyze the image, you extract the features. And then you put them for search, indexing, blah, 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 into an image database, right? So this is the offline part. And now comes the online part, because you are the user, you are here, right? And you have an information need, right? You want to know something. So you have a query, for example, about a certain image. You want something that is similar to an image you have in mind. For example, my wonderful Mona Lisa. Right? And you want to look for that. So you have to do kind of like the same thing. You have to digitize it, so you can kind of like transport the image information. You have to analyze it and do the feature extraction, right? And now comes the interesting part. You have to do a similarity search of what you have digitized and what you have analyzed with the whole image database that has been prepared, right? And that gives you the original Mona Lisa of Leonardo da Vinci, right? Here she is, and comes back to you, and then you are happy and smile like the Mona Lisa, right? Because you now know everything you wanted to know about the Mona Lisa. So this is how it works coarsely. If we look into more detail, what we find is that the offline part down here, right? So this is offline. Just says, well, I insert all the images that I want to have be searchable into the database, right? And what I do is I have the actual objects, the image files, and I may have some relational data. This is by Leonardo da Vinci. This was painted in 1431 or whatever, right? And this is so on. I insert it into the database. With the relational data, that's easy, right? Table, name of the painter, date, blob, right? And the blob is the actual image information. Now I have it in the database, but I can only query by the relational data because I can't interpret the blobs. So I need something more. I need the extraction of the features from the raw data, right? And I put that in a searchable form next to my table that contains the actual relational information, right? The query, like before, prepares the query object and has to extract the same feature values that I'm using in the database, right? So the interface has to match. And then there's the similarity computation between the feature values and the query plan, for example, for relational data or for, has to be shifted around in the typical query processing that we do in normal databases, right? Has to be optimized, there has to be a physical plan, blah, blah, blah. The normal thing that we did in classical databases, right? These results have to be put together, and then you have to prepare the result for digestion of the user, right? So how do you show images? Do you just write, oh, there's the Mona Lisa by Leonardo da Vinci, or do you show a small image of it, right? Or do you deliver the full-size thing, right? What do you do? Different possibilities. In any way, you give back the result, and the user may decide whether new queries are needed or whether he or she is happy or whatever. So this is kind of like the online part, right? Good. Even more detailed views. Multimedia object, relational data. Relational data directly goes into a relational database. Classical tables, right? Dum 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 dum. Multimedia database contains the blobs. Here's another word for you, clobs or C-lobs, character large objects, texts, right? Also uninterpreted. Of course, what you need to do, you need to work on it to extract the features. They need some pre-processing. They need a decomposition. You have to take the images apart, for example. They have to be normalized. You have to kind of like, does it matter whether images are in different resolutions or in different sizes, right? Or is that, with respect to the content that they are showing, not important? Maybe you have to segment certain images to look for, oh, there's a tiger standing on the image, or there's something that is elephant shaped on that image, right? Something like that. With all these information, you build the features. You extract the features, right? Once you decided what is important in the terms of semantics of an image. And after you extracted them, you need to index them because you want fast access, right? You don't want to kind of like compare feature to feature. You want to say, okay, I want everything that is close to this feature, right? Give me the top 10 matches from the database now, right? So feature indexing, very important thing. Okay, same for the query, right? Again, you need the normalization, segmentation, feature extraction to get the feature values, and you need the optimization of the query plan. You get the normal relational stuff that you do anyway. And then you have the similarity computation, right? Showing you, okay, this is more similar, this is less similar, plus the normal query processing built on the databases, right? Then you get the results data, where you may prepare the results by transforming the video or the format. So you can have small images, for example, instead of the big ones for the result presentation in a very low resolution, so the people can get the optic impression, but not yet the full resolution. And when they click on it, they get the full resolution delivered afterwards, right? Saves a lot of bandwidth basically in doing that, and a lot of time too. Okay, then the user gets the result, and there's another important thing that it's not, okay, this is the result, that's it, right? But the user may be happy with the result or less happy with the result, right? It's not like the bank account or the current balance of Gerd Müller, right? Where you can't be happy about it or not, right? It's kind of, it's a fact, you know, like it's there. But in this case, the user can say, well, these are actually not similar in the sense that I meant similar, right? I wanted something that is more similar in the colors, you know, like this is all different images by tigers, you know, like they all show tigers, or they are all by Monet, but they are different from what I actually wanted. I wanted images that are more similar in terms of the color, or in terms of the sujet that they paint, or in terms of the genre. I just wanted expressionist pictures or something like that, right? So that's kind of like relevance feedback that then goes directly into the similarity computation and can change parameters in that computation, or even change features, ignore some features, weigh other features higher. Good? So this is kind of like the detailed view of what we're trying to do. And that brings us to our detour, and we will talk about the applications of multimedia databases today. Break afterwards?
Hello everyone, I'm Younes, and I'm gonna introduce you to the detour. So, as the name suggests, just relax and listen to what I have to tell. Basically, the content of this part is not relevant for the examination. It mostly to give you more detail about some algorithm, how those algorithms are working, to give you also some historical background about some concept, and to have a better understanding about how this multimedia database discipline has evolved across the age. So now we will deal with the application related to multimedia database, and basically the interest is to see that multimedia database is quite awesome, and you are actually making good choice in following this lecture. But first, we are surrounding with multimedia content as long as we are connected to the web. We will interact with multimedia content via social networking, and basically a lot of you, I guess, are using Facebook or MySpace. I don't know if MySpace is still popular. Are some of you using MySpace?
Still online, but no one actually uses it.
Yeah. Because I remember that in 2006 it was quite popular. You have got a lot of artists that had those blog and sharing some of their songs, like DJ and so on. Some of you may share a picture with the rest of the world with image database platform like Flickr or Instagram and Picasa. So Flickr at the moment is hosting about 6 billion image, and so it's used by random user like us, and also by professional photographer. And some of you like watch their favorite video on YouTube. Some of you like listening to their favorite song via Spotify and some audio streaming platform. So basically, the idea is that we are surrounded with multimedia content as long as we are connected to the web. But we are also surrounded with this type of content in our daily life basis. And so if we look, we are constantly filmed by camera. And a very interesting fact is that in London you have got about 500,000 cameras, which is quite huge, and which means that a random pedestrian who is having fun in walking in the street might be filmed about 300 times a day. And so if we imagine a control center room, so you have got this guy who is monitoring the activity around the activity of the street, and if he has noticed a very suspicious activity like this woman here, who is stalling from this girl, well, having this configuration, it will be quite hard for this guy to follow this girl across those different monitors. And so it is a challenge. He needs to find her across those different monitors. He needs to recognize her across the crowd, and he needs to know where those cameras are located. So it's a big task. And we need, as computer scientists, we need to help him supporting this task. And so basically a solution would be face recognition, and to provide him a tool that is able to recognize people thanks to facial feature, like for instance the distance between the eyes, or the size of the nose, the size of the lips, and so on. And a very popular tool is Picasa, and so Picasa, it's a software which is used for managing your photo and also for sharing the content with Google. And so you will see, and so basically they have a face recognition feature, and you will see that it's quite useful. So I'm gonna make now just a simple demonstration. I just hope that that will work. So I'm gonna upload some pictures, so which are here. So it was a trip organized.
It's my holiday photos. Come on.
So we're gonna analyze them. So imagine that you are traveling with someone, and you are taking a lot of photos, and your friend is asking you, okay, I want the picture, but I want only the picture where I appear. I'm not interested in the other picture. So you will have to look at all the pictures, you will have to sort them, and it's quite long, a long task. So with this tool, we're gonna see the magic. So I'm gonna upload my picture. And I'm gonna make sure that face detection option is activated. So now let's see what's happened. It's scanning, so the faces are scanned. And so at the end, the system has been able to recognize the face within the different picture. And so what is interested is, for instance, here is Christoph, which is former colleague. So if I want to find all the picture related to Christoph, I'm just gonna add a name. So, oops, so it's already here. So here, basically, I'm going to get all the picture with Christoph. And so on. And yeah, what you can see is that, for instance, here, it didn't recognize that it was Christoph. But usually it worked pretty well. And yeah, it's quite interesting, and it helps you to organize your picture in a better way.
But you see that there's even different lighting, you know, like in wearing glasses and not wearing glasses and so on. So it is kind of good, right?
Yeah, it's it's able to recognize someone based on side photo and front photo, which is it's quite nice. So here, and I can organize and I can submit all the picture related to Christoph. So in 2007, it was at an early stage. So at the beginning, it didn't work well. I mean, the average rate of correctness was about 30%. So the system was able to recognize someone with well, yeah. So it was not so good. And only 7 years later, now a system is able to recognize someone with 89% of chance. So actually, there are some researchers from the university in Hong Kong that have made the challenge that a computer system will outperform a human. So to make some comparison, a human has about 97% of chance of recognizing someone correctly. And so basically you have got a system that is outperforming human, which is quite amazing. So if some of you are interested in, there is a paper, and I think that, yeah, the algorithm is called Gaussian face.
We will link the paper on the website, so you'll find all the resources on the website.
So it's quite powerful, it worked pretty well, and so it's able to recognize quite easily the face and to organize and to cluster the different picture according to the face. So there are a lot of things to do with multimedia database, and here we're going to see a very sample scenario. So just imagine that we have got like a very huge police investigation, something like Breaking Bad or Scarface. Yeah, I hope that you know. No? Yeah. And so basically, the nice thing with multimedia database is that it provides you a lot of heterogeneous information that will help you to identify something. And so basically in this case, we are looking for the leader of a cartel, like, I don't know, like Tony Montana in Scarface or Heisenberg in Breaking Bad. And so we have manifold data which will help us. So we have got video data provided by camera. We have got audio, like for instance, recordings, conversation between some suspect. We have got image data, which is consisting of photograph, which have been taken by some investigator. We have got some structural relational database data, so some text information with I don't know if we have got our criminal, we have got some information like their record, when they have been caught, when they have, how long have been they in jail, which type of crime had they done, and so on. And we have got geographic information system data, which will help us to find out where Tony Montana is located. And then with such, if you try to merge that in some multimedia database, we need to have some search functionality. And we have different type of queries that we can express to our system. And basically, the idea of query is that we are conveying our information need through some text, we can have image query, we can have different type of query, but basically it's it's for conveying our information need. And so we can first, so if we have some idea about who is the leader of the Carter, we may have a photograph or something like that, and we want to get more picture of him. So the first thing to do, we can query the database by keyword. So basically, I can say, okay, send me all the picture which are labeled or are annotated by this string Tony Soprano. But that supposes that all the pictures are manually are annotated, are linked with some metadata describing those pictures. Another image query would be by example. So I've got a picture here, and I know that this guy is Tony Montana. So what I can say to my system, I say, okay, based on this picture, I want you to retrieve all the picture where this guy appears. Another type of query would be, for instance, related to a murder case. So when there is a murder, I don't know, some police officer can make some hypothesis, some assumption, like before the victim get killed, he was followed few days before by his murderer, or some stuff like that. And so basically with video query we can say, okay, send me all the video where the victim appear. So for instance here, Jerry has been killed, but we are trying to find who is the murderer. So we are asking the system, and then he submits us different video. So we can see that Jerry is followed by Tom. Here you've got Tom, who is harming Jerry, and so we start to gather a lot of clue, a lot of hints that will help us to detect who is the murderer. And at the end, we will be able to claim that Tom is the murderer and arrest him. And in a perfect world, what we want to have at the end is to combine all those different type of query. And basically, we want to submit to the system a heterogeneous multimedia query where we are connecting different features. We can connect audio feature with image feature and so on. So for instance here, I want to find the leader of my cartel, who is Tony Soprano. So what I'm gonna, and I don't know, Tony Soprano has ordered a few days ago a murder of someone. And so I want to see if Tony Soprano is involved in this murder. So basically what I can say, okay, show me all the individual that has been photographed with Tony Soprano. And so here I rely on image feature, and then who have been convicted of attending murder in New Jersey. So here we are relying on some local geographical information, here maybe on textual information or something related with structural relation database. And I want to see if those guys who has been found have received recently a huge transfer on amount from the Paint account of Tony Soprano. So it's quite interesting, and so we have seen that we have got a heterogeneous way to ask for something, but multimedia database have also a heterogeneous characteristic. So we have got about 6 dimensions. So a multimedia database can have static configuration, so high number of search query, few modification of the data. So if you remember, I was using Picasa, and well, the only thing I have to do is to query the picture, and there was no change in the picture. They're still the same, nothing happens, the data is still the same, the only thing I'm doing is I'm querying, and that's all. Another dimension is that multimedia database can be dynamic. So basically, well, here it's on the opposite, the data is constantly changing. So for instance, if we are monitoring the activity of a suspicious pedestrian, well, we will notice that over the time, well, he is walking, and then he starts running, and then he sits next to a tree. And so basically, we're going to exploit those change of states to make some analysis. So here, we are handling some data that are changing over the time. A passive database is when it's kind of database that is waiting that the user is submitting a kind of signal or a request or a query. But for instance, if I come back with my Picasa example, well, my system was waiting that I'm submitting some kind of signal. But I can, for instance, open it, work with it someday, and then I stop, and a few days later I come back to work with. I will notice that the system won't do anything until then. At the opposite, a system can be active. So basically, here the idea is that the system is trying to do things by itself. It doesn't need the input of a user. So for instance, well, if a system has detected suspicious activity, and so basically the idea would be such a system would automatically provide, so if I come back with my example with so camera, and you have got this control center with a lot of screen. So an active system would be a system that, for instance, is tracking a suspicious activity and has found that there is someone that is quite strange, or is murder, or some stuff like that. So an active system would be a system that detects that and submits this information to our police officer, for instance. Standard search, which is pretty used by Google Image. So basically you are looking for some kind of multimedia content, mostly based on some metadata. So instead of extracting some feature from the content, well, what you're gonna look is the keyword or the surrounding text which is related to the image. And so, and the last dimension is that retrieval functionality. And so, typical example, for instance, it was face recognition. So here, let's see an example of passive static retrieval. So what I have, I've got some image, I've got some painting like this one, and I have, let's assume that all those paintings are tagged with a coat of arms. Yeah, with some coat of arms. And in my database, what I have I've got this coast of arm, and I've got some additional information like, okay, this coast of arm belonged to the family. I don't know if some of you like watch Game of Thrones. You have got all this family, and you have got this coast of arm. And so basically, you start, you upload a new picture, and you don't have any idea of who is this guy. And you want to find, maybe to have a hint or to know to which family he belonged to. So you have a hint here, which is this coast of arm, and you will exploit this feature in order to find out to which family he belonged to. So basically what you need to do, you need to first pre-process, and you need to extract the coast of arm. So you don't care of all around the image, you are interested in getting that. And then another step which is quite important is to extracting this pattern here, which is a branch with 3 leaves. And so you're going to do that for the image, and you're going to do that and you're going to match this new information with the other image, which has been also already pre-processed. For the same thing, for the other, just pre-process, we try to catch the coast of arm, and we try to detect this pattern. So we're going to make a matching, and we're going to compare, and at the end, we're going to have some additional information, so for instance, like text, and basically, we're going to try to exploit that to know to which family he belonged to. But actually, it's quite challenging because you can see the shape of the coast of arm is quite different, and the displaying, so basically, of this pattern is different. It's displaying other sense, or so in our perfect multimedia-based system, we would hope a system that would be able to consider all those parameters for finding the family of this guy. And so basically it's passive because the system is waiting us for query, he's waiting us for submitting a signal, and it's quite static because the only thing you are doing is comparing image, so nothing changes over the time, the images are still the same. Another example would be, for instance, using multimedia database for detecting typhoon based on satellite picture. And basically, in this example, we are using, so the weather is quite dynamic. I mean, it's always changing over the time. And so here we are handling some pictures that are constantly changing. And basically, what is the purpose of the system is, as soon as it has been able to detect a typhoon, it will automatically submit a message to the weather station of the country that is endangered by this typhoon. So, and so basically, actually, it's a challenge because it needs to recognize that this country here is Philippines, and he needs to recognize that a typhoon starts to occur and start to threaten this country. Now, very typical search which is commonly used by Google and Google Image, so it's search through the metadata. So basically, you are only looking to the surrounding text related to this image. So for instance, if I'm querying volatile, so I get this image, but you can see, for instance, this one has nothing to do, or I mean, it's just the institute where we are working. And so also this one here, Dr. Vol, Sieberski. So it is easy to implement, but sometimes it didn't work well. And maybe we can rely on face recognition system, but the problem is that Google is handling billions of images, so trying to implement such a system would be very hard and very costly. And so again, as I've doing the demonstration of Picasa, retrieve some content based on some retrieval functions. So for instance, like face recognition. Okay, so this is the end of this detour, and I think we're gonna make 10-minute breaks.
Okay, let's go on then. So, for the last part of the lecture, I want to talk about evaluation of systems, because talking about retrieval system, whether something is wrong or something is not so good, is an important point, right? It's not like in SQL databases where you can say either or, you know, like either it is correct or it's not correct, but there's a degree of correctness, there's a degree of similarity, so it has something to do with the degree. And there's always two kinds of measures. So one is the efficiency of the system, and the efficiency has something to do with the utilization of resources, especially time, you know, like how long do you have to wait for results, how long does it take the system. It has something to do with scalability too, right? Scalability, how many pictures can you put into a database, right, until the face recognition breaks down finally, and so on. The second part is not concerned with the efficiency, but rather with the effectivity. So, I mean, you can do something very quick with a very low effectivity, so it's quick but wrong, right, which you don't want. On the other hand, you can do something that takes for ages, but then is very, very correct or very clear-cut what it will be. So effectivity usually talks about the quality or the meaningfulness of the result that you get, right? And it's very hard to say which one is more important or how you should balance them. There are two aspects that always need to be considered, right? And you want usually something that is in the middle, not the quick and dirty thing and not the very slow but correct thing, but something that is in the middle and is good enough, right? Fast enough and good enough, right? And also there you have kind of like different things to look at. So if you want to evaluate efficiency, usually you're talking about memory usage, you're talking about CPU times, you're talking about IOs and how many IO load you have, and at the end you're talking about response time, right? So how long does the user have to wait? And of course, that's something that strongly depends on the hardware environment. When you try to do something on your smartphone, it will probably take longer than on the new IBM supercomputer, right? Obviously, that's the case. So you somehow have to bind it to the hardware, and especially for multimedia databases, there are special servers. How many? Or special servers that are used for specific applications. And if you look at graphic processors in computers, they can carry heavy loads, right? So they're kind of like very strong entities, and that has a reason. So in any case, we want a system that is fast enough, that is efficient enough. Effectivity, on the other hand, is a little bit more difficult because we can't just measure the time that elapsed from clicking and submitting the query, right, until the first results pop up, right? But we have to look at what is correct and what is incorrect, right? And usually what is correct depends very strongly on the query that you're posing. Some queries might be very, very unique or very easy to interpret. Some queries might be ambiguous or might like have different meanings. And then you cannot say, okay, this result is wrong because it is not exactly the meaning that you wanted, right? So it's kind of tricky, and to really get objective quality metrics is very difficult, because mostly an impression, or especially similarity, right, is a very subjective thing. But for comparing between different systems, you need objective measures. Yeah? So you have to objectivize it somehow, right? And of course, the effectivity, or determining the effectivity, should be independent from the interfaces and the retrieval procedure. Only then you can allow you can compare between different algorithms running in the background, right? You need to be quite sure what is right or what is wrong, or what is wanted or what is not wanted, and then you can build algorithms that actually get you there, right? Good. The effectivity thus has to be measured using any query, and usually not only a single query, but a set of queries, and then you take the average over the correctness, or how good it actually is, right? So the relevance of the result set, and the big point here is relevance with respect to the query, should be determined in advance, independently of the system, only with respect to the semantic content of the collection and the query on the other side, right? And this is usually called a gold standard, or the ground truth, right? And building these things is kind of difficult, right? Because as it is a subjective feature, some things people would agree on, some things even different raters or different evaluators would not agree on that. So usually you also have measures like the inter-rater consistency to figure out whether this was a task that all raters considered to be clear-cut, like it's obvious that pictures A, B, C are the best ones, and D to Z are rotten to the core, or was that a task where one reviewer said, yeah, A and B are kind of good, but then there's also E, right? And the other reviewer said, well, A was good, B was not so perfect, and X was fantastic, right? And so if the raters actually agree, shows you a lot about the semantics that involved in the task, right? The more ambiguous the semantics, the less inter-rater agreement you will have usually, right? So if you do an evaluation of different algorithms against each other, look at your ground truth, look at your gold standard, and look at the inter-rater agreement. If it sucks, then the evaluation probably sucks, right? So that's kind of like, indeed. So we will not look at implicit information needs for the rest of the lecture. So there are some ways, user profiling and so on, to kind of like get the actual information need, the actual information content from users. But that is a different kind of lecture. That is user knowledge, user modeling and knowledge representation. That is not part of this lecture here. We will talk more about algorithmic relevance and what algorithms can do. Okay, relevance as a measure for retrieval comes in two flavors in a way. So you can have a binary classification. A document is relevant with respect to the query, or it's irrelevant, right? This classification is usually done by experts and by raters. You see the inter-rater agreement as the clarity with which something can be classified as being relevant or irrelevant. and the response of the system has then to match the classification as done by the experts, right? And the more the system calls relevant, which is irrelevant, the worse the system is, and the more relevant things the system misses out on, the worse the system is, right? So you're looking at these, you're kind of comparing to the ideal result that the raters would have chosen, given that they know all the different images or the videos or whatnot, right? Second flavor of relevance is that of the ranking, right? So you can compare different rankings to each other and say, this is better than that and this is better than that. This is something that we will also not cover in the lecture. There's a lecture on information retrieval and web search engine. In these cases, it's much more important to talk about rankings, to talk about sequences of information. Good. The involved set, when you talk about a binary sense of being relevant or being not relevant, is what you actually searched for. So all the relevant items that have been stated by experts looking through the whole collection as being relevant with respect to the query queue, right? And then you have what your system retrieves, right? So the system says this is relevant with respect to query queue, and more often than not, there is an intersection between them, right? And the larger the intersection, the better the system is, because it covers it more and more, covers the sense of the experts, right? And the more lost space is, so things that are found that are deemed irrelevant by the experts, the worse the system is, right? So you want this area to be very big, and you want this area to be very small. That makes the quality, the effectivity of a system. And of course, we have names for that, so we're talking about about positives and negatives, right? And we're talking about falsely retrieved items and correctly retrieved items, and now they come in all kinds of combinations. So there are the false positives or false alarms, where irrelevant documents that are classified as relevant by the system have been found. So this is this part over here, the false positives. And the less of them you have, the better it is, because they just increase the result set, right? On the other hand, there's usually some ambiguity in the system, so you will have some of them. And the advantage of having false alarms or false positives is that you retrieve them, you put them into the result set, and the user can then kind of look through them and say, oh, no, I don't want that, I don't want that. I see where it's coming from, but I don't want it, right? So they can be sorted out quite easily. It's not a big problem. A kind of like more dangerous problem is so-called false negatives or false dismissals. False dismissals are all the relevant objects that are deemed relevant by experts that you would expect in the set, but that are not retrieved by the system. And that is a difficult set because you cannot sort them out. You don't see them. They are in the big database, but you don't see them. So you don't know whether they exist or not, right? So this is a little bit more dangerous. So if you have to decide for a system having more false alarms or more false dismissals, right? You'd rather go for the one that has less false dismissals. On the other hand, I mean, I can easily build a system that has no false dismissals by just giving back the whole set, right? Then I have a lot of false alarms, but no false dismissals. This is also not sensible. The whole amount of objects that you're handing back to the user, of course, plays a role for the effectivity of a system. So if I have to look through volumes and volumes of possibilities, right, then this is not a very sensible thing. We know from user studies with web search engines, for example, that hardly anybody looks behind the second side of what Google puts out, right? Hardly anybody. You have to be very eager to get something, and you have to know that it's there, or you have to kind of suspect.
That's why Google changed the interface. I mean, now I don't know if it's in the German Google, but in the English one, you don't have anymore to click at the second page, but only by scrolling down you get to the second.
Okay, clever. Yeah, it's really.
Because no one looks at the
Yeah.
second page, that's why.
Yeah, that's exactly the case here. So you should keep the retrieved set small, avoid false dismissals, and avoid false alarms, however, with less priority. This is what I'm trying to say. Good. Of course, there are the remaining sets, the correct positives. Haha, very good. This is what we all love. This is what we all want. And the correct negative. Nobody could care less about what is around these sets, right? They are just for this query not important, not relevant, right? So all these sets are disjoint, and the reunion is the entire document collection, right? So they build up the document collection. So and now we can kind of like look at the confusion matrix that is existing. So the effectivity of an algorithm can be looked at by looking at the system evaluation versus the user evaluation or the expert evaluation, right? So what is deemed relevant by the expert and relevant by the user are the correct alarms, right? Or true positives. They are very relevant, you want to have them. What is deemed relevant by the user but not found by the system are the false dismissals. Very dangerous, right? Keep them small. What is deemed irrelevant by the user or by the expert and deemed relevant by the system are the false alarms. To a smaller degree, because you can sort them out afterwards, at least you have seen them, right? So avoid them, but not by all means. And then you have the correct dismissals, everything that is irrelevant or deemed irrelevant, as well by the experts as by the system, right? So, good thing. The relevant results are the false dismissals and the correct alarms. They are usually handpicked by experts, and this is called a gold standard, right? Or the ground truth, right? And there are several such sets for different tasks. So there's, for example, for face recognition, there's different sets where images are annotated, whether this is actually the same person or not, and you can test your algorithms on these sets. The retrieved results are the correct alarms and the false alarms. That is everything that is shown here in red. And if you go to the measuring of the whole thing, then you have usually two measures. One is the precision, and the precision measures the ratio of correctly returned documents relative to all returned documents. So the correctly returned documents relative to all returned documents, right? How many of the documents that are actually returned as a result set are indeed relevant? This is the precision or the accuracy of the set. And you get a value between 0 and 1. So if you have no correct alarm in your result set, then you get 0. And if 100% of the result set is perfectly correct, is perfectly relevant, right, then you get the precision of 1. If you get higher numbers of false alarms, you get smaller values for the precision, obviously. Good. The recall measures the ratio of correctly retrieved documents relative to all relevant documents. So how many of those documents that are actually relevant in the results did you get? Right? So basically it is the correct alarms in comparison to what? False dismissals, yes. So in proportion to the false dismissals, what you actually searched for. Again, 100% perfect overlap, good system. Recall of 1. 0%, you didn't get anything that was expected, yes, that was relevant. So the higher the number of false drops, the worse the results are. Okay? Good. Precision recall are antagonistic measures, because I can usually, by making the result set smaller that I deliver, I deliver only the top item that I'm very sure about. Very high precision, right? Terrible recall. On the other hand, I can tune it the other way. I retrieve everything, right? Very high recall. Precision sucks, right? So you can see that there are easy ways to play around with these measures. Usually you have to optimize both of them at the same time to get a good retrieval system, right? So really at the same time. And this is kind of like the balancing that the system has to do, where the system has to be sure, should I put in some more results to improve the recall with the danger of hurting precision? Or should I leave some out with the danger of hurting the recall, but to improve precision, right? And that has something to do with the confidence value of the system. And then you look at the average precision recall of several queries, of a set of queries over the gold standard, right, that have been handpicked. And this is the average performance, the average effectivity of the system. Okay? Good. So the actual evaluation that you do is you look at the alarms, right? And divide them in correct alarms and false alarms. Since you have a gold standard, you can easily look that up. So the precision is easy to calculate. With the dismissals, it's a little bit more difficult. So the recall is difficult to calculate, because usually this set of false dismissals, the things that are correct but that you don't see, are not retrieved. So how do you know they are there? Of course, in a gold standard, you know, like they have been marked up, right? But in a normal set, on the web, I have no idea how much I'm missing out, because I have no idea what is actually there, right? Does Google tell me the whole truth? Or are there wonderful pages that Google just misses out on for whatever reason, right? And this is something, so recall is sometimes difficult to calculate, right? It is, of course, if you have a gold standard, both things are easy to calculate, and this is why people use standardized benchmarks for that, where the queries are provided, where the connections to the result set are provided with high inter-rater consistency, right? So that you have a good benchmark to compare different systems, compare different result sets to each other. Brought you an example. So if you have a query, right, and you have two queries, here's a query that has 8 false alarms and 2 correct alarms, and 6 false dismissals and 4 correct dismissals, and we end up with a precision of 0.2 and a recall of 0.25, right? If we have a second query, we might have much higher rates, right? So we see the false dismissals are much lower here, right? And the correct alarms are much higher here. So we end up in both higher precision and recall, right? And then we can compute average precisions, 0.5 here, or 0.5, right, for this system. And now we can compare it to other systems running exactly the same kind of queries over the same image collection and see what they do on average, right? Good. So you build it then as so-called precision recall curves. You have the recall down here from 0 to 1. You have the precision up here from 0 to 1. And at different points in recall, you examine the precision of the system, right? So you go over different 20% recall, 40% recall, 50% recall. How high is the precision, right? And then you get a curve. So for example, for system 1 here, what you see is this is system 1. This is system 1. What you see is that the system has very high precision values for low recall. So this is a system that gives small result sets at a very high precision, right? So they are mostly correct. You will have hardly any false alarms. On the other hand, you're missing out quite a lot, because down here, the precision goes down quite strongly, right? On the other hand, you might have a system like this over here. So this system maintains a rather high precision over different recall levels, right? So it seems to be a system that delivers quite a lot from the beginning, because the precision already is 80% even for 10% of recall, right? So it seems to rather give back more results, but on the other hand, it stays even at higher recall levels at a good precision. So it seems to perform better if you're interested in high recall, whereas the other system performs better if you're interested in high precision, right? So you cannot say, very often you cannot say, this system is better than the other one, right? If their precision recall curves at some point intersect. They have a different behavior. Of course, if you had a system that is up here, right? That is better than all of these three systems at all counts, right? Because it is better in precision at every recall level. Perfect system. And moreover, it is quite normal that with raising recall levels, precision goes down, right? Because you're collecting more and more false drops, which negatively affects the precision, right? Good. Everybody understood what this is about? Everybody understands how to evaluate a retrieval system and what are the differences to classical SQL style systems? Yes? Then that was all for today. Next lecture, it will be colorful. So next lecture, we are diving into some of the features so we start at image processing, and some of the features that are connected to image processing are the color of images, and they transport a lot of mood and so on. So we will talk about how to represent color and how to build good color features, right? Thank you for the attention. Yes. After he cut it and edited it, and then it will be online.